Chapter 3. The Elements of Vectorial Algebra and Analysis, Scalars and Vectors. Section 97. Ordinary algebra, as is well known, treats of quantities and their relations. If, however, we examine geometry, we shall soon find that the fundamental entity concerned, namely a straight line when regarded as an entity, cannot be treated simply as a quantity in the algebraical sense. It has indeed size, viz., its length, but with this is conjoined another important property, its direction. Taken as a whole, it is a vector. In contrast with this, an ordinary quantity having size only is a scalar. Again, if we consider the mathematics of physical questions, we find two distinct kinds of magnitudes prominently present. All such magnitudes as mass, density, energy, temperature are evidently quantities in the simple algebraic sense, that is, scalar magnitudes or simply scalars. A certain, it may be an unstated unit of density, for instance, being implied, any density is expressed by a simple number. The question of the dimensions of physical magnitudes is not in question. All magnitudes whatever, which have no directional peculiarity, and which are each specified by a single number, are scalars and subject to scalar algebra. But such magnitudes as displacement, velocity, acceleration, force, momentum, electric current, etc., which have direction as well as size, and which are fully specified by statement of the size and direction, are vector magnitudes, or simply vectors. Now, just as there is an algebra and analysis for scalars, so is there a vector algebra and analysis appropriate to vectors, and it is the object of the present chapter to give a brief account of the latter, especially in respect to its application to electromagnetism. Characteristics of Cartesian and vectorial analysis. Section 98. Algebraical or analytical geometry in the usual Cartesian form, though dealing ultimately with vectors, is not vectorial algebra. It is, in fact, a reduction to scalar algebra by resolution of every vector into three rectangular components, which are manipulated as scalars. Similarly, in the usual treatment of physical vectors, there is an avoidance of the vectors themselves by their resolution into components. That this is a highly artificial process is obvious, but it is often convenient. More often, however, the Cartesian mathematics is ill-adapted to the work it has to do, being lengthy and cumbrous, and frequently calculated to conceal rather than to furnish and exhibit useful results and relations in a ready manner. When we work directly with vectors, we have our attention fixed upon them and on their mutual relations, and these are usually exhibited in a neat, compact, and expressive form, whose inner meaning is evident at a glance to the practiced eye. Put the same formula, however, into the Cartesian form, and what a difference! The formula, which was expressed by a few letters and symbols in a single line, readable at once, sometimes swells out and covers a whole page. A very close study of the complex array of symbols is then required to find out what it means, and even though the notation be thoroughly symmetrical, it becomes a work of time and great patience. In this interpretation, we shall, either consciously or unconsciously, be endeavoring to translate the Cartesian formulae into the language of vectors. Again, in the Cartesian method, we are led away from the physical relations that it is so desirable to bear in mind to the working out of mathematical exercises upon the components. It becomes, or tends to become, blind mathematics. It was once told as a good joke upon a mathematician that the poor man went mad and mistook his symbols for realities, as M for the moon and S for the sun. There is another side to the story, however. If our object be ultimately physical rather than mathematical, then the more closely we can identify the symbols with their physical representatives, the more usefully can we work, with avoidance of useless, though equally true, mathematical exercises. The mere sight of the arrangement of symbols should call up an immediate picture of the physics symbolized, so that our formulae may become alive, as it were. Now, this is possible, and indeed comparatively easy in vectorial analysis, but is very difficult in Cartesian analysis, beyond a certain point, owing to the geometrically progressive complexity of the expressions to be interpreted and manipulated. Vectorial algebra is the natural language of vectors, and no one who has ever learnt it, not too late in life, however, will ever care to go back from the vitality of vectors to the bulky inanimateness of the Cartesian system, abstrusity of quaternions, and comparative simplicity gained by ignoring them. Section 99. But supposing, as is generally supposed, vector algebra is something awfully difficult, involving metaphysical considerations of an abstruse nature, only to be thoroughly understood by consummately profound metaphysico-mathematicians, such as Professor Tate, for example? Well, if so, there would not be the slightest chance for vector algebra and analysis to ever become generally useful. And I should not be writing this, nor should I have, for several years past, persisted in using vector algebra in electromagnetic theory, a prophet howling in the wilderness. It will readily be concluded, then, that I believe that the vector analysis is going to become generally used in scientific work, and that is not awfully difficult. There was a time, indeed, when I, although recognizing the appropriateness of vector analysis in electromagnetic theory and in mathematical physics generally, did think it was harder to understand and to work than the Cartesian analysis. But that was before I had thrown off the quaternionic old man of the sea who fastened himself on my shoulders when reading the only accessible treatise on the subject, Professor Tate's Quaternions. But I came later to see that, so far as the vector analysis I required was concerned, the quaternion was not only not required, but was a positive evil of no inconsiderable magnitude, and that by its avoidance the establishment of vector analysis was made quite simple and its working also simplified, and that it could be conveniently harmonized with ordinary Cartesian work. There is not a ghost of a quaternion in any of my papers, except in one, for a special purpose. The vector analysis I use may be described either as a convenient and systematic abbreviation of Cartesian analysis, or else as quaternions without the quaternions, and with a simplified notation harmonizing with Cartesians. In this form, it is not more difficult, but easier to work than Cartesians. Of course, you must learn how to work it. Initially, unfamiliarity may make it difficult, but no amount of familiarity will make quaternions an easy subject. Maxwell, in his great treatise on electricity and magnetism, whilst pointing out the suitability of vectorial methods to the treatment of his subject, did not go any further than to freely make use of the idea of a vector in the first place, and to occasionally express his results in vectorial form. In this way, his readers became familiarized with the idea of a vector, and also with the appearance of certain formulae when exhibited in the quaternionic notation. They did not, however, derive any information how to work vectors. On the whole, I am inclined to think that the omission of this information has not tended to impede the diffusion of a knowledge of vector analysis. For, had he given an account of the theory, he would certainly have followed the Hamilton-Tate system, and this would probably, for reasons I shall shortly mention, have violently prejudiced his readers against the whole thing. But the diffusion of vector analysis has undoubtedly, in my opinion, been impeded by the absence of sufficiently elementary works on the subject, with a method of establishment of principles adapted to ordinary minds, and with a conveniently workable notation. For the reader of Maxwell's treatise who desired to learn to work vectors in analysis had either to go to Hamilton's ponderous volumes or else to Professor Tate's treatise. The former are out of the question for initiatory purposes, but the latter is excessively difficult, although described as an elementary treatise, not the same thing as a treatise on the elements. The difficulty arises in a great measure from the quaternionic basis, round the quaternion. The laws of vector algebra themselves are established through quaternions, assisted by the imaginary root -1. But I'm not sure that anyone has ever quite understood this establishment. It is done in the second chapter of Tate's treatise. I never understood it, but had to pass on. That the establishment is not demonstrative may be the reason of the important changes made therein in the third edition. But it is still undemonstrative to me, though much improved. Now this relates to the very elements of the subject, vis a terra, the scalar and vector products of a pair of vectors, the laws of which are quite plain in the Cartesian mathematics. Clearly, then, the quaternionic is an undesirable way of beginning the subject, and impedes the diffusion of vectorial analysis in a way which is as vexatious and brain-wasting as it is unnecessary. Tate and Gibbs versus Tate, section 101. Considering the obligations I am personally under to Professor Tate, in spite of that lamentable second chapter, it does seem ungrateful that I should complain. But I have at heart the spread of a working knowledge of elementary vector analysis, quite as much as Professor Tate has the extension of the theory of quaternions. Besides, Professor Tate has assumed a very conservative attitude in relation to Hamilton's grand system. For instance, to more than one correspondent who had written for explanation of something they found obscure, and the same thing occurred to me, he described in his treatise by, "It is evident, ... He, on full consider, decides not to modify it, but to italicize the words. He also told them that if they did not see it in the light of certain preceding parts of the treatise, then they had begun the study of Quaternions too soon." Third edition, page 110. This is as characteristic of the sardonic philosopher as a certain heavy kind of flippancy is of the Cockney. Again, in his preface, he states one cause of the little progress made in the development of quaternions to be that workers have, especially in France, been more intent on modifying the notation or the mode of presentation of the elementary principles than in extending the application of the calculus. Even Professor Willard Gibbs must be ranked as one of the retarders of quaternionic progress, in virtue of his pamphlet on vector analysis, a sort of hermaphrodite monster, compounded of the notations of Hamilton and Grassmann. Grassmann, I may observe, established, inter alia, a calculus of vectors, but not of quaternions. Professor W. Gibbs is well able to take care of himself. I may, however, remark that the modifications referred to are evidence of modifications being felt to be needed, and that Professor Gibbs's pamphlet, not published, New Haven, 1881, 4 pages 83, is not a quaternionic treatise, but an able and in some respects original little treatise on vector analysis, though too condensed and also too advanced for learners' use, and that Professor Gibbs, being no doubt a little touched by Professor Tate's condemnation, has recently, in the pages of Nature, made a powerful defense of his position. He has, by a long way, the best of the argument, unless Professor Tate's rejoinder has still to appear. Professor Gibbs clearly separates the quaternionic question from the question of a suitable notation, and argues strongly against the quaternionic establishment of vector analysis. I am able, and am happy, to express a general concurrence of opinion with him about the quaternion and its comparative uselessness in practical vector analysis. As regards his notation, however, I do not like it. Mine is Tate's, but simplified and made to harmonize with Cartesian's. Abolition of the minus sign of quaternions. Section 102. In quaternions, the square of a unit vector is -1. This singular convention is quaternionically convenient. But in the practical vector analysis of physics, it is particularly inconvenient, and being indeed an obtrusive stumbling block. All positive scalar products have the minus sign prefixed. There is thus a want of harmony with scalar investigations, and a difficulty in readily passing from Cartesians to vectors and conversely. My notation, on the other hand, is expressly arranged to facilitate this mutual conversion. As regards the establishment of the elementary vector algebra, that is quite simple, free from the quaternion. It all follows from the definitions of a vector and the scalar and vector products of a pair of vectors. Now I can imagine a quaternionist, unless prejudiced, admitting the simplicity of establishment and of operation, and the convenience of the notation, and its sufficiency for practical requirements up to a certain point, and yet adding the inquiry whether there is not, over and above this vector analysis, a theory of quaternions which is overlooked. To this I would reply, certainly, but it is not food for the average mathematician, and can, therefore, never be generally used by him, his practical requirements being more suitably satisfied by the rudimentary vector analysis divested of the mysterious quaternion. This does not exclude the important theory of the nabla and its applications. Professor Gibbs would, I think, go further and maintain that the anti- or ex-quaternionic vector analysis was far superior to the quaternionic, which is uniquely adapted to 3 dimensions, whilst the other admits of appropriate extension to more generalized cases. I, however, find it sufficient to take my stand upon the superior simplicity and practical utility of the ex-quaternionic system. We may, however, if we wish to go further, after ex-quaternionic establishment of vector algebra, conjoin the scalar and vector, and make the quaternion, and so deduce the whole body of quaternions. But sufficient for the day is the labor thereof, and we shall now be concerned with scalars and vectors only. The reader should entirely divest his mind of any idea that we are concerned with the imaginary root -1 in vector analysis. Also, he should remember that unfamiliarity with notation and processes may give an appearance of difficulty that is entirely fictitious, even to an intrinsically easy matter, so that it is necessary to thoroughly master the notation and ideas involved. The best plan is to sit down and work. All that books can do is to show the way. Type for vectors: Greek, German, and Roman letters unsuitable. Clarendon type suitable. Typographical backsliding in the present generation. Section 103. We should, in the first place, fix how to represent vectors, although in reality this is the outcome of experience. A vector may obviously be denoted by a single letter, and having defined certain letters to stand for scalars and others for vectors, it is certainly unnecessary that the vectors should be distinguished from the scalars by the use of different kinds of types. But practical experience shows that it is very desirable that this should be done in order to facilitate the reading of vectorial work by showing at a glance which letters are vectors and which are scalars, and thus easing the stress and strain on the memory. This is all the more important because the manipulation of vectors sometimes differs from that of scalars. Now, Professor Tate usually indicates vectors by Greek letters, but it is well known that a considerable familiarity with the Greek letters, such as is acquired by studying the literature of ancient Greece, is required before they can be read and manipulated with facility. On the other hand, few are Greek scholars, and in fact many people think it is about time the dead languages were buried. Greek letters are, at any rate, not very well adapted to a vector analysis, which aims at practical utility. Maxwell employed German or Gothic type. This was an unfortunate choice, being by itself sufficient to prejudice readers against vectorial analysis. Perhaps some few readers who were educated at a commercial academy where the writing of German letters was taught might be able to manage the German vectors without much difficulty. But to others, it is a work of great pains to form German letters legibly. Nor is the reading of the printed letters an easy matter. Some of them are so much alike that a close scrutiny with a glass is needed to distinguish them, unless one is lynx-eyed. This is a fatal objection. But irrespective of this, the flourishing ornamental character of the letters is against legibility. In fact, the German type is so thoroughly impractical that the Germans themselves are giving it up in favor of the plain Roman characters, which he who runs may read. It is a relic of medieval monkery and is quite unsuited to the present day. Besides, there can be little doubt that the prevalent short-sightedness of the German nation has, in a great measure, arisen from the character of the printed and written letters employed for so many generations by inheritance and accumulation. It became racial, cultivated in youth, it was intensified in the adult, and again transmitted to posterity. German letters must go. Rejecting Germans and Greeks, I formerly used ordinary Roman letters to mean the same as Maxwell's corresponding Germans. They are plain enough, of course, but as before mentioned, are open to objection. Finally, I found salvation in Clarendon's and introduced the use of the kind of type so called, I believe, for vectors, Philosophical Magazine, August 1886, and have found it thoroughly suitable. It is always in stock, it is very neat. It is perfectly legible, sometimes alarmingly so, and is suitable for use in formula along with other types, Roman or italic, as the case may be, contrasting and also harmonizing well with them. Sometimes block letters have been used, but it is sufficient merely to look at a mixed formula containing them to see that they are not quite suitable. I should mention here, however, that it is not the mere use of special types that converts scalar to vector algebra. For instance, engineers have often to deal with vector magnitudes in their calculations, but not, save exceptionally, in their vectorial signification. That is, it is merely their size that is in question, and when this is the case, there is no particular reason why a special kind of type should be used, whether blocks or another sort. In connection with Clarendon type, a remark may be made on a subject which is important to the community in general. I refer to the retrograde movement in typography, which has been going on for the last 20 years or so. Many people who possess fairly good and normal eyesight find a difficulty in reading printed books without straining the eyes, and do not know the reason. They may think the print is too small, or that the light is not good, or that their eyes are not right. But the size of type per se has little to do with its legibility. A far more important factor is the style of type, especially as regards the fineness of the marks printed. The old style, revived a generation since and now largely in use, differs from the more legible modern style of this page, for instance, in two respects. It has certain eccentricities of shape which make it somewhat less easy to read. But more importantly, the letters on the type are cut a good deal finer, which results in a pale impression as if the ink were watery. This is the main cause of the strain upon the eyes and the good light wanted. Even very small print is easy to read if it be bold and black, not thin and pale. It would be a public benefit if the retrograde step were reversed, and the revived old style, which threatens to drive out the modern style, discarded. Not that the latter is perfect. A still better style would be arrived at by thickening the fine lines in it, producing something intermediate between it and the Clarendon style, which last, of course, would be too much of a good thing. As everyone who has had to read manuscripts knows, the most legible handwritings, irrespective of the proper formation of the letters, are those in which the writing master's fine upstroke is discarded. Now it is the same in print. Thicken the fine lines and the effect is magical. Notation: tensor and components of a vector. Unit vectors of reference. Section 104. The tensor of a vector is its size or magnitude apart from direction. Other important connected quantities are its three rectangular scalar components, the Cartesian components, which are the tensors of the three rectangular vector components. It is usual in Cartesian work to use three separate letters for these components as F, G, H, or U, V, W, or Xi, Eta, Zeta, etc. One objection to this practice is that when there is a large number of vectors, the memory is strongly taxed to remember their proper constituents. Another is the prodigal waste of useful letters. One alphabet is soon exhausted and others have to be drawn upon. In my notation, the same letter serves for the vector itself and for its tensor and components. Thus, E denoting any vector, its tensor is E, and its components are E1, E2, E3. Similarly, the tensor of A is A, and the components are a 1, a 2, a 3. A large stock of letters is thus set free for other use. But a remark must be made concerning manuscript work, as distinguished from printed work. In manuscript work, it is inconvenient to be at the trouble of writing two kinds of letters. Ordinary letters will suffice for both scalars and vectors, or the ordinary letters representing vectors may receive some conventional mark to vectorize them. But, presuming ordinary letters are written, something is required to distinguish between the vector and its tensor. This may be satisfied by calling E0 the tensor of E. Only when an investigation is to be written out for the printers is it necessary to bring in special letters, and this is most simply done by a conventional mark affixed to every vector. Compositors are very intelligent, read mathematics like winking, and carry out all instructions made by the author. If a vector A be multiplied by a scalar x, the result, written xa or ax, is a vector x times as big as A and having the same direction. Thus, if A1 be a unit vector parallel to A, or more strictly, parallel to and concurrent with A, of unit length, we have A equals A times A1. It is sometimes useful to separately represent the direction and length of a vector, and the above is a convenient way of doing it without introducing new letters. This applies to any vector, but it need not be an absolute rule. For instance, the Cartesian coordinates x, y, z of a point may be retained. Thus, let r be the vector from the origin to any point, and let I, j, k be unit vectors from the origin along the three rectangular axes. We shall then have x equals xi, y equals yj, z equals zk, equation 1, where x is the vector projection of r on the I-axis, as we know by the elementary geometry of a rectangular parallelepiped or brick. Also, the direction cosines of r are x over r, y over r, z over r, and r squared equals x squared plus y squared plus z squared. Equation 2 by Euclid 1:47. The addition of vectors. Circuital property. Section 105. This brings us to vector addition. The vector x signifies translation through the distance x in the direction I. If now, after performing this operation, we carry out the operation indicated by y vis terra, translation through the distance y in the direction j, and lastly, carry out the operation z, or translation through the distance z in the k direction, we shall arrive at the end of the vector r. That is, starting from one corner of a brick, we may reach the opposite corner by 3 mutually perpendicular journeys along 3 edges of the brick. The final result is the same as if we went straight across from corner to corner, that is, by carrying out the operation indicated by the vector r. This equivalence is expressed by r equals x plus y plus z, equation 3, or by equation 1, r equals xi plus yj plus zk, equation 4. The meaning of addition of vectors in this example is simply the carrying out of the operations implied by the individual vectors added, the geometrical vector meaning a displacement in space or translation from one point to another. The order of addition is indifferent since there are 6 ways of going from one corner to the opposite one of a brick along its edges. We see that any vector may be expressed as the sum of 3 mutually perpendicular vectors, vis itera, its vector projections on the axes. Furthermore, by the use of a skew parallelepiped instead of a brick, we see that any vector may be expressed as the sum of 3 other vectors, having any directions we please, provided they are independent or not all in the same plane. For in the latter case, the parallelepiped degenerates to a plane figure. But it is perhaps best to explain vector addition in general without any reference to axes. Thus, let A and B be vectors to be added, A meaning translation from P to Q in the first figure, or through an equal distance along any parallel line, as from S to R in the second figure, whilst B means translation from Q to R in the first figure, or through an equal distance along any parallel line, as from P to S in the second figure. In the first case, performing the operation of first, and then B, we go from P to R via Q. In the second case, with B first and then A, we go from P to R via S. The final result in either case is equivalent to direct translation from P to R, symbolized by the vector C. Thus, C equals A plus B equals B plus A, equation 5. The above may be extended to any number of vectors, or we may reason thus. Let A be any given vector, translating, say, from P to Q. We need not go from P to Q direct, but may follow any one of an infinite number of paths, as for example A plus B plus C plus D in the figure. The final result of the successive translations is always the same, vis itera, the direct translation A, or A equals A plus B plus C plus D, equation 6. Thus, any vector A may be split up into the sum of any number n of vectors, of which n minus 1 are perfectly arbitrary, for instance A, B, C in the figure. The remaining 1D is, of course, not arbitrary. It is the vector required to complete the circuit of vectors. The vectors need not be in one plane, nor need the path followed consist of finite straight portions. It may be wholly or partly curved. The curved portions are then made up of infinitesimal vectors. Each curved portion may be replaced by the vector joining its terminals. Since the original vector and the substituted vectors form a circuit, if the positive direction in the circuit be the same for all the vectors, we may express vector addition thus. The sum of any number of vectors which make a circuit is 0. That is, sigma A equals 0 if A is the type of the vectors summed. For a curved circuit, we shall have integral of ds equals 0, equation 7, where ds is the vector element of the circuit. Here S itself may be taken to be the vector from any fixed point P to a point Q on the circuit, figure 4. Then ds is the infinitesimal change in S made in an infinitesimal step along the circuit. That is, it is the vector element of the circuit itself. In a vector equation, every term is a vector, of course. However, the individual terms may be made up, and every vector equation expresses the fact symbolized by equation 7, or by sigma A equals 0 when the vectors are finite. In the latter case, A may be also regarded as delta S, the finite change in the vector S from any fixed origin produced by passing from beginning to end of the vector A. The minus sign prefixed to a vector is the same as multiplication by -1, and its effect is simply to reverse the direction of translation, or it may be regarded as reversing the tensor without altering the direction. Thus, minus A equals minus A1 equals A times minus A1 equals minus minus A times A1, equation 8. Thus, in any vector equation, for example, A plus B plus C plus D plus E plus F equals 0, equation 9, we may transfer any terms to the other side by prefixing the minus sign. Thus, A plus B plus C equals minus D minus E minus F, F equals minus of D plus E plus F, equation 10. In the form 9, we express the fact that translation in a circuit is equivalent to no translation. In 10, however, we express the equivalence of two translations by different paths from one point to another. If any trouble be experienced in seeing the necessary truth of 9 for a circuit in whatever order the addition be made, the matter may be clinched by means of I, J, K, the unit rectangular vectors. As we saw before, the resolution of vectors into rectangular component vectors depends only upon the properties of the right-angled triangle. Thus, split up the vectors a, b, c into components. We have a equals ia, 1 plus j, a2 plus k, a3, b equals ib1 plus jb2 plus kb3, c equals ic1 plus jc2 plus kc3, equation 11. Now add up all vectors parallel to I add in scalar fashion, for there is no change of direction. Similarly for j and k, so we have a plus b plus c equals I of a1 plus b1 plus c1 plus j of a2 plus b2 plus c2 plus k of a3 plus b3 plus c3. Now the scalar additions may be done in any order we please. It follows that the same is true in vector addition. The addition and subtraction of vectors and transfer from one side of an equation to the other are thus done identically as in the algebra of scalars. Addition has, it is true, not the same meaning, but the vector meaning is not inconsistent with the scalar meaning, and in fact includes the latter as a particular case. There is never any conflict between plus put between vectors and plus put between scalars. Notation: tensor and components of a vector. Unit vectors of reference. Section 104. The tensor of a vector is its size or magnitude apart. Futility of popular demonstrations. Barbarity of Euclid. Section 106. In the above, we have referred entirely to the geometrical vector, but a very important step further can be made, referring to physical vectors, a step which immediately does away with piles of ingeniously constructed and brain-wasting demonstrations, especially compiled for the torturing of students and discouragement of learning. If a quantity be recognized to be a directed magnitude, it is, in its mathematical aspect, a vector, and is therefore subject to the same laws as the vector or geometrical vector. So, just as we have the triangle or parallelogram or polygon of geometrical vectors, we must have the same property exemplified in the addition of all vectors as velocity, acceleration, force, etc. This identity of treatment applies not only to the addition property, but to the multiplication and other properties to be later considered. We may symbolize a physical vector by a straight line of given length and direction. It used to be thought necessary to give demonstrations of the parallelogram of forces, perhaps even before the student knew what force meant. I have some dim recollection of days spent in trying to make out de Cila's proof, which was certainly elaborate and painstaking, though benumbing. Maxwell, in his treatise, elaborated a demonstration that electric currents compounded according to the vector law. But surely there is something of the vicious circle in such demonstrations. Is it not sufficient to recognize that a quantity is a vector, to know that it follows the laws of the geometrical vector, the addition property of which does not want demonstrating, but only needs pointing out, as in the polygon of vectors? Although this is not the place for exercises and examples, yet it is worthwhile to point out that by means of the addition property of vectors, a good deal of geometry can be simply better than by Euclid, a considerable part of whose 12 books consists of examples of how not to do it, especially Book 5. There is a Society for the Improvement of Geometrical Teaching. I have no knowledge of its work, but as to the need of improvement there can be no question whilst the reign of Euclid continues. My own idea of a useful course is to begin with arithmetic, and then, not Euclid, but algebra. Next, not Euclid, but practical geometry, solid as well as plane, not demonstrations, but to make acquaintance. Then, not Euclid, but elementary vectors conjoined with algebra and applied to geometry. Addition first, then the scalar product. This covers a large ground. When more advanced, bring in the vector product. Elementary calculus should go on simultaneously and come into the vector algebraic geometry after a bit. Euclid might be an extra course for learned men like Homer, but Euclid for children is barbarous. The scalar product of two vectors. Notation and illustrations. Section 107. Coming next to the products of vectors, it is to be noted at the beginning that the ordinary idea of a product in arithmetic and in scalar algebra does not apply to vectors, because they are not scalars. We cannot, therefore, say beforehand what the product of two vectors ought to be, or determine this question by any prior reasoning of a legitimate nature. We must examine in what way vectors enter into combination as products, and then introduce definitions and conventions of notation to give expression to the facts in the simplest and most convenient way. After this, the work is deductive. By this examination, we are led to recognize two distinct kinds of products of a pair of vectors, the scalar product and the vector product. It is with the former of these that we are now immediately concerned. We define the scalar product of a pair of vectors a and b whose tensors are a and b and whose included angle is theta to be the scalar ab cosine theta, and we denote it by a dot b. Thus, a dot b equals ab cosine theta. This is equation 12. This defines the scalar product and its notation. To see its full significance and how it works out, let us first apply equation 12 to the unit reference vectors I, j, k, which are perpendicular by taking a and b to be one or other of them in turn. First multiplying each of I, j by itself, we get I squared equals 1, j squared equals 1, k squared equals 1. This is equation 13. With the convention borrowed from scalar algebra that I is equivalently denoted by I squared, this may be called the square of I. In each of the three cases in equation 13, the vectors multiplied together are of unit length and are parallel and concurrent so that the scalar product, according to equation 12, is unity. Similarly, the square of any unit vector is unity. And since a dot a equals a squared, the square of any vector is the same as the square of its tensor, or a squared equals a squared. This is equation 14. Also, the scalar product of any two parallel vectors is the product of their tensors. For a dot b equals ab times plus or minus 1, and a dot b is now unity. Next, make scalar products of I, j, k in pairs. We get I dot j equals 0, j dot k equals 0, k dot I equals 0. This is equation 15. That is, the scalar product of two perpendicular unit vectors is 0. The same is of course true of any two perpendicular vectors. Thus the equation a dot b equals 0 means that a is perpendicular to b, unless indeed one or other of them is 0. We have also a1 dot b, 1 equals cosine theta. This is equation 16. By dividing equation 12 by ab, or the scalar product of any two unit vectors, is the cosine of the included angle. This is reckoned positive from concurrent coincidence, so that as theta goes from 0 to 2 pi, a1 dot b, 1 goes from 1 through 0 to minus 1, and then through 0 again to plus 1. There is strictly no occasion to introduce trigonometry. Or we might make the trigonometry be a simultaneously developed subject. It is in fact a branch of vectorial algebra, being scalar developments of parts thereof. We may employ the idea of perpendicular projection simply. Thus, we may say that the scalar product of a pair of unit vectors is the length of the projection of either upon the other, and that the scalar product of any vector A and a unit vector I is the projection of A upon the axis of I. And comprehensively, that the scalar product A dot B of any two vectors A and B is the product of the tensor of either into the projection, perpendicularly upon it, of the other. It is the effective product, so to speak. In physical mathematics, scalar products frequently have reference to energy or activity or connected quantities. Thus, if F be a force and V the velocity of its point of application, their scalar product F dot V is the activity of the force. It is the product of the speed and the effective force. When the force and the velocity are perpendicular, the activity is nil, although the velocity may be changing, a fact which familiarity does not render less striking. When F and V are parallel, whether concurrent or not, F dot V becomes the same as FV in the common meaning of a product. A notation that harmonizes in this way is obviously a convenient one. Notice also that A dot B equals B dot A, as in scalar algebra. A frequently occurring operation is the surface integral of the normal component of a vector, for example, to express the amount of induction through a surface. Here, the idea of a unit normal vector n is useful. The normal component of b is then n dot b, and the integral is the integral sign n dot b, the summation extending over the surface. Similarly, to express the line integral of the effective component of a vector along a line, we may let t be the unit element of curve, that is, the unit tangent. Then t dot e is the tangential component of the vector e, and the integral sign t dot e is the integral. For example, the voltage between 2 points along the path to which the summation refers, if E be the electric force. Since a dot B is a scalar, it behaves as a scalar when considered as a whole. Thus, when multiplied by a scalar x, the result xa dot b, or a dot b times x, is scalar, being simply x times a dot b. When multiplied by a vector, the result is a vector. Thus, ca dot b, or a dot bc, means a dot b times the vector c. The dot here acts rather as a separator than as a sign of multiplication. Thus, to illustrate, ca dot b means c times the scalar a dot b. And similarly, a dot bc is bc times the vector a. But instead of the dot, we may use brackets to indicate the same thing. Thus, ca dot b may be written c a dot b. This is perhaps preferable in initiatory work, but I think the dot plan is more generally useful. We have an example of this combination of three vectors in the stress formula. Thus, the electric stress vector on the plane whose unit normal is n is expressed by E dot d times n minus 1/2 E dot d times n, equation 31, section 72. That is, the sum of two vectors, parallel to E, the electric force, and to n, respectively, whose tensors are E dot d and minus 1/2 E dot d, respectively, where d is the displacement. The interpretation as a tension along E combined with an equal lateral pressure obtained by taking n parallel to and then perpendicular to E or D has been already discussed. Fundamental property of scalar products and examples. Section 108. As all the preceding is involved in the definition of a scalar product and is obvious enough, it may be regarded merely as illustrative. The reader might in fact say that he knew it all before in one form or another, trigonometrical or geometrical, and that he did not see any particular advantage in the way of stating it in the notation of scalar products. But we now come to a very striking and remarkable property of scalar products, which will go far to justify them as working utilities. We know that in scalar algebra, when we have a product xy, we may express x by the sum of any number of other quantities, and similarly as regards y, and then obtain the complete product xy by adding together all the component products obtained by multiplying every element of x into every element of y, and that this process may be carried out in any order. Now, in vector algebra, we know already that there is a partial similarity, viz. That we can decompose a vector A into the sum of any number of others, and similarly as regards B. The question now is whether the scalar product AB is the sum of all the scalar products made up out of the components of A paired with the components of B, taken in any order. For example, if A equals A plus B and B equals C plus D, is AB equals A plus B times C plus D. That is, equals AC plus AD plus BC plus BD. This is equation 17. The answer is yes, and the process of manipulation is the same as in scalar algebra, that is, as if all the vectors were scalars. Moreover, this property admits of demonstration in a sufficiently simple manner as to enable one to see its truth. Start with the vector A, and first split it up into equals A plus B plus C. This is equation 18, 2 or 3 vector components being sufficient for illustration. Now project the vector A perpendicularly upon any axis, say that of I. According to our definition of a scalar product, the projection is A dot I. Now it requires no formal demonstration, but becomes evident as soon as the meaning of the proposition is correctly conceived, that the projection of A upon any axis is the same as the sum of the projections of its component vectors, A, B, C, on that axis. That is, the latter projections are either all positive or all negative and fit together to make up the projection of A, or else some may be negative and others positive when there is overlapping and canceling, but still with the same result algebraically. This is expressed by A dot I equals A plus B plus C dot I equals A dot I plus B dot I plus C dot I. This is equation 19 got by multiplying equation 18 by I. If we now multiply equation 19 by any scalar b, so that bi equals b, which is any vector, since I may have any direction, we obtain ab equals ab plus bb plus cb. This is equation 20, the same as if we multiply equation 18 by b direct. Similarly, we may split up b into the sum of any number of other vectors, say b equals d plus e plus f. This is equation 21. If we substitute this in equation 20, we have ab equals a times d plus e plus f, plus b times d plus e plus f, plus c times d plus e plus f. Now make use of the same reasoning which established equations 19 and 20, applied to the bracketed vectors, and we establish the property fully, with the result AB equals A plus B plus C times D plus E plus F equals AD plus AE plus AF plus BD plus BE plus BF plus CD plus CE plus CF. The expansion being done formally as in scalar algebra in every respect, since the various terms may be written in any order and each may be reversed, thus AD equals DA. I've already remarked that a good deal of geometry may be done by the addition property alone. The range of application is greatly extended by the use of the scalar product and the fundamental property just stated. To obtain the Cartesian form of AB, put the vectors in terms of I, J, K. Thus AB equals A1I plus A2J plus A3K times B1I plus B2J plus B3K. This is equation 22. Now effect the multiplications, remembering equations 13 and 15. The result is AB equals A1B1 plus A2B2 plus A3B3. This is equation 23. For example, the activity of a force is the sum of the activities of its component forces in any three perpendicular directions. Or, if A and B are unit vectors, we express the cosine of the angle between them in terms of the products of the direction cosines of the vectors, each product referring to one axis. In equation 23, we may, if we please, factorize the 6 scalars on the right side. Since the square of a vector is the square of its tensor, we may express the tensor at once in terms of the tensors and the cosines of the angles between a series of vectors into which the original vector is resolved. Thus, for 2, a plus b squared equals a squared plus 2ab plus b squared. This is equation 24. A minus b squared equals a squared minus 2ab plus b squared. This is equation 25. And similarly for 3, a plus b plus c squared equals a squared plus b squared plus c squared plus 2ab plus 2bc plus 2ca. This is equation 26. Here equations 24 and 25 apply to a parallelogram and equation 26 to a parallelepiped. In equations 24 and 25, if a and b be the vector sides of a parallelogram, then a plus b and a minus b are the vector diagonals. So equation 24 gives the length of one diagonal and equation 25 that of the other. Adding equations 24 and 25, we obtain a plus b squared plus a minus b squared equals 2 times a squared plus b squared. This is equation 27, expressing that the sum of the squares of the diagonals equals the sum of the squares of the four sides. Similarly, by subtraction, a plus b squared minus b squared equals 4ab. This is equation 28, expressing the difference of the squares of the diagonals as 4 times the scalar product of two vector sides. Equation 27 also shows that the sum of the squares of the distances of the ends of any diameter of a sphere from a fixed point is constant. For if A is the vector from the fixed point to the sphere's center, and B the vector from the center to one end of the diameter, then A plus B and A minus B are the vectors from the fixed point to the ends of the diameter. Whence by equation 27 the proposition. There is an application of this in the kinetic theory of gases. For when two elastic spheres collide, they keep the sum of their kinetic energies constant. If, then, their velocities before collision be a plus b and a minus b, their velocities after collision are indicated by vectors from the origin in the velocity diagram to the ends of some other diameter of the sphere described upon the line joining their original positions in the velocity diagram as diameter, which is actually the new diameter depending upon the circumstances of impact. Reciprocal of a vector. Section 109. It is occasionally useful to employ the reciprocal of a vector in elementary vector algebra. We define the reciprocal of a vector A to be a vector having the same direction as A and whose tensor is the reciprocal of that of A. We may denote the reciprocal of A by a to the minus 1 or 1 over A. Thus, as A equals A1 times A, we have A to the minus 1 equals 1 over A equals A 1 over A. This is equation 29. Any unit vector is, therefore, its own reciprocal. The reciprocal of a vector being a vector makes scalar products with other vectors. Thus, ab to the minus 1 or a over b means the scalar product of a and b to the minus 1, and we therefore have a over b equals ab to the minus 1 equals a1, a over b1 equals a b over b squared. This is equation 30. The tensor of a over b is a over b cosine theta, where theta is the angle between a and b, or between their reciprocals, or between either and the reciprocal of the other. So a over a, or a to the minus 1, or a to the minus 1a equals unity. In using reciprocals, the defined meaning should be attended to, especially when put in the fractional form. Thus, we easily see that a b to the minus 1 equals ab over b squared, because the tensor of b is b times the tensor of b to the minus 1. But we cannot equivalently write a squared over ab, because this is a over b cosine theta, which is quite a different thing. Notice that a to the minus 1, b to the minus 1 is not the same as ab to the minus 1. The first is a to the minus 1, b to the minus 1 cosine theta, whilst the latter is a to the minus 1, b to the minus 1 cosine theta. Expression of any vector as the sum of three independent vectors. Section 110. We know that in the equation r equals xi plus yj plus zk, where r is the vector distance of a point from the origin, the scalars are the lengths of the projections of r upon the axes. How should we, however, find them in terms of r algebraically? To find x, we must operate on the equation in such a manner as to cause the j and k terms to disappear. Now this we can do by multiplying by I, for I is perpendicular to j and k, so that multiplication by I gives ri equals xi squared equals x. Similarly, rj equals y and rk equals z. From this obvious case, we can conclude what to do when the reference vectors are not perpendicular. For instance, in r equals fa plus gb plus hc, equation 31, where a, b, c are any independent vectors. To find f, we must multiply by a vector perpendicular to b and c, say L, so that LB equals 0 and LC equals 0. Then RL equals FAL, therefore F equals RL divided by AL. Similarly to isolate G and H, so that we get R equals RL over AL times A plus RM over BM times B plus RN over CN times C. Equation 32, where L, M, N are vectors normal to the three planes of BC, CA, and AB. This exhibits explicitly the expansion of any vector in terms of any three independent vectors A, B, C as the three edges of a skew parallelepiped. This case, of course, reduces to the preceding Cartesian case by taking A, B, C to be I, J, K, when L, M, N will also be I, J, K, or any scalar multiples of the same. Observe the peculiarity that auxiliary vectors are used, each of which is perpendicular to two others, to the plane containing them. These auxiliary vectors bring us to the study of the vector product. The vector product of two vectors. Illustrations. Section 111. The auxiliary vectors just employed in the expansion of a vector into the sum of three vectors, having any independent directions, are examples of vector products. Two vectors being given, their vector product is perpendicular to both of them. Of course, disregarding magnitude, there is but one such vector, vis terra, the normal to the plane containing the given vectors. Nor is the tensor of any consequence in the example in question, for it will be observed that one of the vectors L, M, N appears both in the numerator and in the denominator of one of the three fractions in equation 32, so that the values of the fractions are independent of the tensors of the auxiliary vectors. But the vector product of two vectors has a strictly fixed tensor depending upon those of the component vectors and their inclination. There is particular advantage in taking the tensor of the vector product of A and B to be a b sine theta. Thus we define the vector product of two vectors A and B, whose tensors are A and B, and whose included angle is theta, to be a third vector C, whose tensor C equals AB sine theta, and whose direction is perpendicular to the plane of A and B. The positive direction of C being such that positive or right-handed rotation about C carries the vector A to B. This vector product is denoted by C equals VAB, equation 33, and its tensor may be denoted by V0AB, so that we have C equals V0AB equals AB sine theta, equation 34. Similarly, V1AB may be used to denote the unit vector parallel to VAB. The only troublesome part is to correctly fix which way along the perpendicular to the plane of A and B is to be considered positive. Examples will serve to clinch the matter. Thus, let A be towards the north and B towards the east on the Earth's surface, then C is straight downwards. Again, in figure 5, the direction of C is downwards through the paper, and its tensor is the area of the parallelogram upon A and B. Let B be fixed whilst A moves round so as to vary the angle theta. Starting from coincidence, when theta equals 0, the tensor of C is 0. It reaches a maximum downwards when theta is a right angle and falls to 0 again when theta reaches 2 quadrants, and A is in the same line with B, though discurrent. After this, in the next two quadrants, the same numerical changes are gone through, but now the sign being negative, C must be upwards from the paper. The unit reference vectors I, j, k are so arranged that when in equation 33, A is I and B is j, then C is k, noting in figure 6 that k is supposed to go downwards or away from the reader. Thus, in accordance with our definition, we have Vij equals k, Vjk equals I, Vki equals j, equation 35, because the mutual angles are quadrants and the tensor's unity. Observe the preservation of the cyclical order ijk in equation 35. Also, we have Vii equals 0, Vjj equals 0, Vkk equals 0, equation 36, because the vectors paired are coincident. By the definition, the reversal of the order of the letters in a vector product negatives it. Thus, VAB equals minus VBA, equation 37. Since the tensor of VAB is a b sine theta and the scalar product AB is a b cosine theta, we have a b squared plus VAB squared equals AB squared, equation 38. Combinations of three vectors. The parallelepipedal property, section 112. A vector product being a vector, of course, combines with other vectors to make scalar and vector products again. Thus, CVAB, where C is any new vector, means the scalar product of C and VAB, and VCVAB means the vector product of C and VAB. These are both important combinations which occur frequently, and their interpretations and expansions will be given presently. As illustrative of notation, it may be mentioned that CV0AB, where, as before explained, V0AB is the tensor, is obviously a vector parallel to C, but V0AB times as long. On the other hand, CV1AB, where V1AB is the unit vector, is the same as CVAB divided by V0AB, since by dividing by its tensor we unitize a vector. Similarly, as regards V1CVAB, we may also have V1CVAB and V0CVAB and various other modifications whose meanings follow from the definition of a vector product and its notation. We do not often go further in practical vector algebra than combinations in threes. For instance, C.VAB, the scalar product of C and the previously explained VAB. The scalar product CVAB has an important geometrical illustration. Its value is given by CVAB equals V0AB times C cosine phi, equation 39, where phi is the angle between C and VAB. This is by the definition of the scalar product and of the tensor of a vector. Now refer to figure 5 again. We know that V0AB is the area of the parallelogram. We also know that the volume of a parallelepiped is the product of its base and altitude. Construct, then, a parallelepiped whose three edges meeting at a corner are A, B, and C. The area of one of its bases is V0AB, and the corresponding altitude is C cosine phi. Therefore, by equation 39, CVAB is the volume of the parallelepiped. But there are two other bases and two other altitudes to correspond, so there are two other ways of expressing the volume, giving the equalities AVBC equals BVCA equals CVAB. Equation 40, in which observe the preservation of cyclical order, done to keep the sign the same throughout, as will be verified a little later. Semi-Cartesian expansion of a vector product and proof of the fundamental distributive principle. Section 113. The semi-Cartesian expansion of C equals VAB is C equals I times A2B3 minus A3B2 plus J times A3B1 minus A1B3 plus K times A1B2 minus A2B1. Equation 41 in terms of I, J, K, and the scalar components of A and B. To prove this, multiply equation 41 by A and B in turns to form the scalar products AC and BC. Do this by the rule embodied in equation 23. We get AC equals A1 times A2B3 minus A3B2 plus A2 times A3B1 minus A1B3 plus A3 times A1B2 minus A2B1. BC equals B1 times A2B3 minus A3B2 plus B2 times A3B1 minus A1B3 plus B3 times A1B2 minus A2B1. But by canceling, all the terms on the right disappear. That is, AC equals 0, BC equals 0. From these, we know that C is perpendicular A and B. It is therefore VAB itself, or a multiple of the same. To find its tensor, square equation 41. We get C squared equals A2B3 minus A3B2 squared plus A3B1 minus A1B3 squared plus A1B2 minus A2B1 squared, equation 42. But this may, by common algebra, be transformed to C squared equals A1 squared plus A2 squared plus A3 squared times B1 squared plus B2 squared plus B3 squared minus a1b1 plus a2b2 plus a3b3 squared. Equation 43, that is c squared equals a squared b squared minus ab squared. Equation 44. Or c squared equals a squared b squared minus a squared b squared cosine squared theta equals a b sine theta squared. The tensor C is therefore that of VAB itself, or else it's negative. Equation 44 is the same as equation 38, in a slightly different form. Equation 41 is proved, except it remains to be seen whether the right member represents VAB or its negative. To do this, we may remark that the angle between two planes is the same as the angle between the normals to the planes, if the normals coincide when the planes do, so that the three quantities in parentheses in equation 41, which are the scalar projections of C on the axes, are also the areas of the projections of the area V0AB on the planes perpendicular to them. We have therefore only to verify that the projection of any plane on the plane null to one of the axes is given correctly in sign by equation 41. Take a rectangle parallel to the JK plane, sides parallel to J and K, that is, a 2J and B3K, so that C equals IA2B3. Here A2B3 is the projection of the rectangle on a parallel plane and is correctly positive. Now go back to equation 41. We have VAB equals I times A2B3 minus A3B2 plus ... equation 45. Similarly, VAC equals I times A2C3 minus A3C2 plus ... equation 46. Add these together. We get VAB plus VAC equals I times A2B3 plus C3 minus A3B2 plus C2 plus ... equation 47. But the right member by definition of a vector product, or by equation 41, means VA of B plus C. That is, VA of B plus C equals VAB plus VAC, equation 48. Similarly, VD of B plus C equals VDB plus VDC, equation 49. So by adding these again, V of A plus D of B plus C equals VAB plus VAC plus VDB plus VDC. Equation 50, a very remarkable and important formula. It shows that the vector product of two vectors, A and B, equals the sum of all the vector products which can be made out of the component vectors, A equals A plus D and B equals B plus C in equation 50, into which we may divide A and B, provided we keep the components of A always before those of B. The necessity of this proviso, of course, follows from the reversal of VAB with the order of A and B. Although equation 50 only shows this for two components to each primary vector, yet the process by which it was obtained evidently applies to any number of components. Subject to the limitation named, the formula 50 is precisely similar to equation 17, section 108, relating to the scalar products. Now, the truth of equation 17 could be seen without much trouble. A similar proof of equation 50, on the other hand, would not be at all easy to follow, owing to the many changes of direction involved in the vector products. This is why I have done it through I, J, K, which are auxiliaries of the greatest value. When in doubt and difficulty, fly to I, J, K. On the other hand, although the establishment of equation 50 by geometry without algebra is difficult, and there is preliminary trouble in fixing the direction of a vector product, yet we see from equation 50 that vector products are nearly as easily to be manipulated algebraically as scalar products. Examples relating to vector products. Section 114. By means of the formula 41, we can at once obtain the Cartesian expansion of the parallelepipedal CVAB. Use equation 23 applied to equation 41, remembering that C is now any vector, and we get CVAB equals C1 times A2 B3 minus A3 B2 plus C2 times A3 B1 minus A1 B3 plus C3 times A1 B2 minus A2 B1, equation 51. By rearrangement of terms on the right side of this, putting the A's outside the brackets, we obtain a VBC, and putting the B's outside, we obtain BVCA, and thus verify equation 40 again. The vector VCVAB is perhaps most simply expanded through IJK. First write D for VAB, then by equation 41, we have VCD equals I times C2D3 minus C3D2 plus ... Next, put for D1, D2, D3 their values in terms of A's and B's, given in equation 41, and we have VCVAB equals I times C2 times A1, B2 plus A3, B3 minus C3 times A1, B2 plus A2, B3 plus ... equals I times A1 times B2, C2 plus B3, C3 minus B1 times A2, C2 plus A3, C3 plus ... Next, add and subtract A1, B1, C1, and we get VCVAB equals I times A1, BC minus B1, AC plus ... Lastly, reconvert fully to vectors, and we have VCVAB equals ABC minus BAC, equation 52. This important formula should be remembered, that VCVAB is in the plane of A and B is evident beforehand, because VAB is perpendicular to this plane, and multiplying by VC sends it back into the plane. It is therefore expressible in terms of A and B, as in equation 52, which shows the magnitude of the components. In some more complex formulae, it is sufficient to remember the principle upon which they are founded, as by its aid they can be recovered at any time. Thus, in the case of R equals FA plus GB plus HC, equation 53 already treated, equation 31, if we use now VBC for L, which is before any multiple of it, and similarly for M and N, we have R equals RVBC over AVBC times A plus RVCA over BVCA times B plus RVA B over CVAB times C, equation 54. There is no occasion to put a formula like this in the memory because it is so simply obtained at any time from equation 53 by multiplying by the auxiliary vectors so as to isolate f, g, h in turn and give their values. Notice that the three denominators in equation 54 are equal. Also, that by exchanging A and VBC, B and VCA, C and VAB, we obtain R equals RA over AVBC times VBC plus RB over BVCA times VCA plus RC over CVAB times VAB, equation 55. And this is also true, as we may at once prove by multiplying it in terms by A, B, and C, each of which operations nullifies two terms on the right. Equation 55 is the expression of R in terms of three vectors, which are normal to the three planes of any three independent vectors A, B, C, taken in pairs. Here again, such a formula can be immediately recovered if wanted by attending to the principle concerned. To obtain the Cartesian expansion of any formula containing vectors is usually a quite mechanical operation. The Cartesian or semi-Cartesian representatives of a few fundamental functions being remembered, their substitution in the vector formula is all that is required. If the formula be scalar, although involving as many vectors as we please, the result is a single scalar formula in Cartesians. But if it be a vector formula, it reduces to a semi-Cartesian vector formula involving I, j, k, giving three scalar equations, one for each component. The converse process, to put a scalar Cartesian investigation into vectorial form, is less easy, though dependent upon the same principles. Here the three-component equations have to be reduced to one vector equation. It is very good practice to take a symmetrically written-out Cartesian investigation and go through it, boiling it down to a vector investigation, using the unit reference vectors I, j, k whenever found to be convenient. The differentiation of scalars and vectors. Section 115. In the preceding account of vector addition and of the scalar product and the vector product, the reader has nearly all that is needed for general purposes in geometry and in the usual physical mathematics involving vectors, so far as the algebra itself is concerned. For the addition of differentiations does not usually introduce anything new into the algebra. Thus, in the analysis of varying vectors, we have the same vector algebra with new vectors introduced, these being derived from others by the process of differentiation. The ideas concerned in the differentiation of a vector with respect to a scalar are essentially the same as in the differentiation of a scalar. Thus, u being a scalar function of x, that is, a quantity whose value depends on that of x, we know that if delta u is the increment in u corresponding to the increment delta x in x, then the ratio delta u over delta x usually tends to a definite limiting value when delta x is infinitely reduced, which limit, denoted by du over dx, is called the differential coefficient of u with respect to x. This I should be strongly tempted to call the differentiation of u with respect to x, were I not informed on the highest authority that the expression differentiation for differential coefficient is objectionable. But the differentiating operator d over dx, which acts on the operand u, may be termed the differentiator, as has perhaps been done by Sylvester and others. This way of regarding a differential coefficient, splitting du over dx into d over dx and u, sometimes leads to great saving of labor, though we are not concerned with it immediately. The differential coefficient is thus strictly the rate of increase of the function with the variable, or the increase of the function per unit increase of the variable, on the tacit assumption that the rate of increase of the function keeps the same value throughout the whole unit increment in the variable as it has for the particular value of the variable concerned. This plan, referring to unit increment, is often very useful. The reservation involved, though it must be understood, need not be mentioned. There is also the method of differentials, which is of some importance in vector analysis, as it can be employed when differential coefficients do not exist. Thus, u being a function of x, whose differential is dx, the corresponding differential of u is du equals f of x plus dx minus f of x, equation 56, which by expanding f of x plus dx reduces to du equals du over dx times dx, equation 57, provided we neglect the squares and higher powers of dx, that is, regard dx as infinitesimal, and therefore du also. And if there be two variables, as in u equals f of x, y, then we have du equals f of x plus dxy plus dy minus f of xy, equation 58, leading to du equals du over dx times dx plus du over dy times dy, equation 59, expressing the differential of u in terms of those of x and y. Now, let the operand be a vector function of x, say e. For instance, x may mean distance measured along a straight line or axis in an electrostatic field, where e, the electric force, will usually change as we pass along the line. It may change continuously in direction as well as in magnitude. In any case, the change itself in e between 2 points on the line is a vector, being the vector delta e, which must be added to the e at the first point to produce that at the second point. Dividing by delta x, the increment in x, we get the vector delta e over delta x. And this, when the increments are taken smaller and smaller, approximates towards a definite limiting vector denoted by dE over dx, which is, by the manner of its construction, the rate of increase of e with x, or the increase in e per unit increase in x. We have also, in differentials, dE equals f of x plus dx minus f of x, equation 60, leading to dE equals dE over dx times dx, equation 61, understanding that the differentials dx and dE are infinitesimal. Similarly, the rate of increase of the vector dE over dx with x is the second differential coefficient d squared, e over dx squared, and so on. Semi-Cartesian differentiation. Examples of differentiating functions of vectors. Section 116. In semi-Cartesian form, we have e equals I, e1 plus j, e2 plus k, e3, equation 62. Here the scalars e1, e2, e3 are functions of x, whilst the reference vectors I, j, k are constants. So we have dE over dx equals I times dE1 over dx plus j times dE2 over dx plus k times dE3 over dx, equation 63, showing the components of the vector dE over dx. Similarly, d squared e over dx squared equals I times d squared e1 over dx squared plus j times d squared e2 over dx squared plus k times d squared e3 over dx squared. Equation 64 shows the components of the second differential coefficient obtained by differentiating equation 63. Now, this semi-Cartesian process is quite general. Any vector function may be expressed in the form 62, and when the right member is differentiated, the differentiations are performed upon scalar functions. The same remark applies to equations 63 and 64, etc. So we see that the rules for differentiating vectors and functions of vectors with respect to scalar variables are the same as those for differentiating similar functions of scalars, so far as the independent action of a differentiator on the separate members of a product goes. Thus, in differentiating a scalar product AB with respect to a variable scalar t, we have, by equation 23, d over dt of AB equals d over dt of a1 b1 plus a2 b2 plus a3 b3 equals a dot b1 plus a2 dot b2 plus a3 dot b3 plus a1 dot b1 plus a2 dot b2 plus a3 dot b3, or retransforming to vectors, d over dt of AB equals a dot b plus ab dot, equation 65, just as if a and b were scalars. Similarly, we have d over dt of VAB equals VA dot B plus VAB dot, equation 66, as we may see immediately by differentiating the semi-Cartesian expansion of VAB, equation 41. We have also d over dt of AVBC equals A dot VBC plus AVB dot C plus AVBC dot, equation 67, and d over dt of VAVBC equals VA dot VBC plus VAVB dot C plus VAVBC dot, equation 68. But although we proceed formally, as in the ordinary differentiation of scalars, as regards the properties peculiar to differentiation, yet we must always remember those which are peculiar to the vector algebra. For example, we must not only on the left sides, but also on the right sides of equations 67 and 68, remember the reversal of the sign of a vector product with the order of the letters. Independently of I, J, K, we may proceed thus, using differentials. D of AB equals A plus DA times B plus DB minus AB equals A DB plus B DA. Equation 69, omitting the infinitesimal dA dB of the second order. Dividing by dt and proceeding to the limit, we obtain equation 65. Similarly, we have d of VAB equals V of A plus dA of B plus dB minus VAB equals VDAB plus VADB, equation 70, omitting the second differential VDADB. So, dividing by dt, we obtain equation 66. In getting equation 69, we have of course used the distributive law of scalar products, equation 17, and in getting equation 70, the similar law of vector products, equation 50.